Thank you. Thank you, everyone. So as you can see, we will continue talking about prediction intervals, and now this time we will focus on adaptivity, and I will explain what it means. So I think, yeah, before we continue, I should say that this talk will focus only on the regression setting, so I won't cover a classification or a time series problems, but we can talk about it later after the talk, if you're interested. Okay, I think it's needless to repeat why we want to build prediction intervals, because previous speakers did a very good job why we need them. So I'll just skip these first slides and jump right into the definition of the prediction interval. Because I think there should be quite a few people in the room who are not familiar with the theory of prediction intervals, so I think it will be still instructive to talk about a little bit of theory behind this. So prediction interval is simply a range of values that contains true value of our target variable with probability of 1 minus alpha. So alpha is called significance level or a miscoverage level in literature, and it's a free parameter, so it's set by us, and let's say if we set it to be 10%, then the corresponding prediction interval is going to contain the true value with 90% likelihood. So very simple notion. So, and again, as previous speakers mentioned, so to build prediction intervals, there is a really nice statistically robust approach called conformal prediction framework. And let's quickly review what it means. So there are a few flavors of conformal prediction, and in this talk we will focus on the one that is most computationally efficient one, and it's called split conformal prediction or inductive conformal prediction. So what it is that we start by splitting our sample into two partitions, training and calibration sets. Then we fit our Bayes estimator. So it's up to us, whatever estimator we want to choose for our project. And the next step is to compute the so-called conformity score. And a conformity score is something that measures the magnitude of the error the model is making. And the important thing is that conformity score is measured on the calibration set and not on the training set. Next step is to estimate 1 minus alpha percentile of the conformity score, and we have this empirical distribution of the conformity score obtained on a calibration set. And finally, we build a prediction interval with this simple expression. So the lower bound of the interval is the prediction at point X minus 1 minus alpha percentile of the score, and the upper bound is the same prediction plus 1 minus alpha percentile of the conformity score. So before we proceed to properties, I think we should focus for the conformal prediction. So first of all, it's a modular approach, which means that you can train whatever algorithm you want, and the only connection between conformal prediction and your algorithm, your model, are the predictions that the model is generating. And the second property that we have to note is that, as you can see, the last expression, conformal prediction, like the standard version of the conformal prediction, provides us with constant widths or constant length intervals. So I will use widths and the length interchangeably, so they mean the same thing. Okay, so let's proceed. So I mentioned that this is a statistically robust framework. So what does it mean? It means that it provides us with guaranteed marginal coverage, and coverage is also known as validity in the literature. So valid prediction interval means that the probability of true value falling in the prediction interval is 1 minus alpha. So then you might ask, what are the requirements from conformal prediction, right? So there is no requirement about the distribution. which is a very strong property of CP, or conformal prediction method. And it provides us with valid prediction intervals in a finite sample setting, and that's also crucial because we have only finite samples in practice, and the only thing that it requires is the exchangeability, or if we reshuffle the order of the samples, then the corresponding joint distribution remains the same. So I must say that exchangeability is a weaker condition than IID. And as you know, most of the statistical algorithms require IID, independent identically distributed samples. And if we assume that we meet that criteria, we can automatically assume that we have exchangeability, which is very neat. So the only thing, important thing that vanilla conformal prediction doesn't provide us with is the conditional coverage. So what does it mean to have conditional coverage, right? So this means that probability of true value falling in the prediction interval given value x is 1 minus alpha. So that's not provided by split conformal prediction, for example. So why we want to have conditional coverage? So we want to have it because we know that our models are not performing homogeneously across feature space. There are some regions in a space, in input space, where model is more confident, and there are regions where model is making larger errors. And we want our prediction intervals to respect that. So we want the width or length of the interval to be adaptive based on what is the magnitude of the error that model is making at a specific point x. So now I think you can understand why we are talking about adaptivity and what it means, and how it is connected with the conditional coverage. So let's talk a little bit more about it to give you an example. If we look at these two graphs, and let's focus on the left one. So this red or a pink strip basically represents a bunch of prediction intervals computed at different values of x. And if you notice, it has a constant width across x, right? But we can also notice that if we look at the scatter plot, that when x is between 1 and 2, we have a much bigger dispersion in the input space, and model is making much larger errors versus a region where x is equal to 3. So regardless of that, split conformal prediction produces still same width intervals. But on the chart on the right, we see completely the opposite. So this blue area, again, represents prediction intervals. And we see that when x is between 1 and 2, the length of the interval is bigger compared to the region when x is equal to 3. So length of the interval is adaptive, and it changes according to the error that model is making. And that's the property that we want to have in our algorithms. The bad news is that it is impossible to achieve exact conditional coverage in finite sample setting. Therefore, there are two types of algorithms developed. The first type is that they try to achieve this conditional coverage in asymptotic regime or in infinite sample regime. And there are other types of algorithms that try to achieve this property locally. So what does it mean to have local conditional coverage? So I said that it is infeasible to have point-wise conditional coverage in a finite sample setting. Therefore, let's partition our feature space into a bunch of subsets. So the capital A represents a partition of a feature space. And let's aim to achieve conditional coverage on the level of the partition instead of having it on a point level. That's what we call local conditional coverage. So next part of the talk is to review the algorithms that provide us with adaptive prediction intervals, or local conditional coverage. So the first one is conformal quantile regression. That one is already implemented in MAPI, and by the way, MAPI is a great library with a nice documentation, so I encourage you, everyone, to use it. And I used it in my experiments as well. So let's review it quickly. So we start with splitting the data. Then we fit two quantile regressors. So if we want to build 90% confidence interval, so we fit the first regressor at 5th percentile and another regressor at 95th percentile. So very simple. Then we compute the conformity score using this expression. Then as conformal prediction teaches us, we have to compute 1 minus alpha percentile of that conformity score. And eventually we will build a prediction interval in this fashion. So the next one that we will review is called locally adaptive conformal prediction. So we start again with splitting, fitting the Bayes estimator, up to us which one it is. And then we compute the conformity score using this formula. So basically it is a residual divided by rho, and rho stands for mean absolute deviation. So depending on, so rho is we have to train rho. It's a standalone model. And if we train rho on the same training sample, let's call that approach weighted ICP, or weighted inductive conformal prediction. And if we fit it on a part of the calibration sample, let's call that approach LCP, local conformal prediction. So basically, conformity score in this case is a weighted residual, where weight is the expectation value of the residual at the same point. So again, then we compute 1 minus alpha percentile, and eventually we will build the prediction interval. And as you can see now, the boundaries now depend on the x through rho, and they become adaptive. Next one that I want to introduce is called low cart or low forest. So this is a family of algorithms, but right now I'll describe the backbone and the idea of the algorithm, and later we can discuss the different versions of it. So after splitting and fitting the Bayes estimator, we compute the conformity score. In this case, it's a simple residual. And then we train decision tree or a random forest on those residuals. So if we train decision tree, we call it low cart, that approach. And if we fit a random forest, let's call it a low forest. So now imagine these black circles are our residuals. So, and I fit a simple two-level decision tree. And what happens is that all those residuals are distributed across these 4 nodes. So basically, training a decision tree on this input space means that we introduce some kind of partitioning of our feature space. Now imagine I have a new test sample and I have to build a prediction interval for that specific point, X test. Then I've trained this decision tree. I can easily identify, therefore, the node this new point belongs to. And if we assume it belongs to the left node, then that left node contains a bunch of residuals, right? And therefore, that node corresponds to a specific distribution of the residual. Then we compute 1 minus alpha quantile of that distribution, and eventually we will build this interval using the same standard expression. So why is this algorithm adaptive? It is adaptive because depending on which node a new test sample belongs to, you have a different percentile. You have a different distribution, residual distribution. Now what happens if we train a random forest instead of a single decision tree on our residuals? So assume we have 100 trees in our random forest. This means that for a single test sample, we have 100 different nodes, one node from one tree. Therefore, one test sample corresponds to 100 different residual distributions, and thus 100 different 1 minus alpha percentiles of those distributions. So eventually we will average out those 100 percentiles, and we will use that single number into this formula of the prediction interval. So that's how it works in case of the random forest. Okay, our next and last algorithm to review is LSF. So it starts by fitting the estimator to the training set, which leaves us with prediction target pairs. So without loss of generality, we can assume that there is a one-to-one mapping between a prediction and a target values, since we are talking about regression problems. And next step is to sort our columns according to the prediction, and I've applied here this gradient color in the prediction column, which means that the points are sorted. So, and then we start grouping our predictions to a point until the point when we reach some predefined number of target values associated with that specific bin. So that predefined number is a hyperparameter of this algorithm. Let's say it is 100. So we group our predictions until they are associated with at least 100 target values. So I guess, you can guess where this is going to, right? So these colorful circles represent prediction bins, and the circles within them represent target values. So therefore, each prediction bin is associated with its own target distribution. And now, let's say I have a new test sample, and I want to build a prediction interval for that test sample. So I already trained my Bayes estimator. I will compute the prediction for that single point, and I can easily identify the prediction bin this single point belongs to. Therefore, I can identify the target distribution corresponding to that bin and calculate the quantiles for that specific target distribution. And eventually, we will build the prediction interval using this simple expression. So please notice that Q has a subscript Y because this quantile refers to the target distribution in contrast to the previous algorithms where we used subscript S for quantile because it refers to the conformity score. So that's why LSF is not part of the conformal prediction framework, because it doesn't work with conformity scores. Okay, so next part and the final part of this talk is the benchmarking of these algorithms. But before we do that, we have to introduce metrics. So we have 3 different metrics for our intervals. So the first one is the width or a length. The smaller it is, we call that it is more efficient. The interval is more efficient. So that's another term from the literature. Of course, we want to have coverage. We want to capture the true value of the target variable using our intervals. And the third property is the adaptivity, the property that we are looking for. So usually if you look at the papers of prediction intervals, so there are you'll see these 2 metrics reported: average interval length and marginal coverage. Marginal coverage is basically, share of the cases where you capture the true value of the target, which is also an average. And it seems that we have this nice measure that combines these 2 into a single number. It's called Winkler score. And here is a definition of the Winkler score. So U stands for the upper bound of the interval, L stands for the lower bound. So if we look at the middle case, so let's assume that true value is captured by the interval, then the Winkler score is simply a length of the interval. But if we fail to capture the true value, then the Winkler score becomes the length plus the error term, the offset. So it's easy to interpret, right? We want to minimize the Winkler score, therefore it penalizes larger intervals and larger errors. So very simple. But remember that we are talking about adaptivity and conditional coverage, and we want to introduce a metric to assess that in our algorithms. So, and if you remember, I mentioned that conditional coverage is sort of associated with the partitioning of the feature space. So, how we should partition the space. And one neat way of doing this is to do partitioning based on the interval length or interval width. Let's assume we build prediction intervals for every sample in our calibration set. Now we compute the widths of every interval, and let's sort our calibration set based on the widths of the interval. And then the next and final step is to create bins. So in this example, I've created 5 different bins based on my calibration set. And in each bin, I estimate the coverage, or let's say, which is basically a share of intervals that actually capture the true value. And our target coverage is 1 minus alpha, right? That's what we want to achieve. So next, we identify the bin with the smallest height, or with the smallest coverage, and that number would be our conditional coverage metric. We want to replicate the same for the Winkler score because it combines coverage as well as the widths of the interval. The only difference is that in this case we compute the average Winkler score in each bin instead of the coverage. So we identify the bin with the smallest height, and the smallest Winkler score would be our conditional Winkler score. So these are the metrics that we will be using to assess our algorithms. So now let's talk about the results. So I've used a bunch of publicly available data sets, and data set that's usually used in the papers to do the benchmarking. So for each data set, I measure the assessment across these 3 dimensions: conditional Winkler score, conditional coverage, and a Winkler score. So Winkler score is based on a marginal coverage, and obviously the main metric for us are the first 2, but just for consistency, I've included the Winkler score as well, the standard Winkler score. So the assessment is done using these critical difference diagrams, or a CD diagram for short, and this horizontal axis in each diagram represents the average rank of the algorithm. The smaller it is, the better is the algorithm. So in this case, low cart is the best one on this data set. And the black horizontal lines connecting different algorithms in the diagram mean that the difference between those connected algorithms is not statistically significant. So then what I do, I just collect the best ones across these 3 dimensions into a table. So I repeat the same process for another data set, collect the results, and so on and so forth. So I do this for other data sets as well, and collect the best ones in a single table. This is also a structured table that you'll see in the papers as well. But I think it's a little bit hard to, again, comprehend and look at these numbers, and it's hard to see which one is on average the best one. So what I decided to do is to aggregate all those experiments across different data sets and to measure the overall performance of our algorithms. So according to conditional Winkler score, the best algorithm is low cart. Basically, tree-based algorithms, or low cart and low forest, also the best ones according to conditional coverage, and same goes true for the simpler Winkler score. So to be honest, I'm not surprised, because we all know that in a regression setting, decision tree-based algorithms still give us the state-of-the-art performance. And as it turns out, the partitioning that the decision tree introduces is the most reasonable one, meaning that it puts the points together in the same node that really have the same distribution and similar quantiles. So there are other algorithms. Yeah, one note. So I mentioned that low cart and low forest is tree-based algorithms. It's basically a family of algorithms. And you can see in the first diagram that a low cart is also a good one. So A here stands for augmented, and it means that instead of a training tree on an original input space, we would do some extra feature engineering to capture the complexity of the feature space, and we will use those features in a training process. So that's what a low cart means. So I've tested a bunch of other algorithms for adaptive prediction intervals, but I did not include them in this experiment. The reason is twofold. So first is that some of them take a lot of time to build the intervals, so inference time is big and becomes it's not practical to use them, especially if you have to build intervals for thousands of points. And another reason I did not include them is that they require the modification of the training loss function. And therefore, they are not easy to implement. And what's more important, we lose the property of modularity of conformal prediction because they require from us to modify the loss function, and you are not. And then this means that you are limited now in terms of choosing which algorithm you want to train for your task. So last note is that, so if you want to start building prediction intervals, now you know where to start from. And if you want to learn more, there is this nice GitHub repo, awesome conformal prediction, and it provides us with up-to-date resources and materials about this field. And please have a look at it if you're interested. So thanks a lot.
We just have a little bit of time for questions. So, is there a question? So, where was it? Sorry. Okay.
Thank you for a very interesting talk. I think this is a very exciting topic. One thing which I'm wondering is when you're using trees or estimators for these adaptive CPs, aren't you sort of pushing the problem somewhere else because you get a point prediction from the predictors that tell you how your confidence interval looks or your prediction set?
Sorry, can you repeat the question? I didn't get it.
So the issue we're trying to solve here is that a typical machine learning model only gives you a point prediction. Yeah. But when you're predicting, in order to determine how wide your prediction sets are, then you have a point prediction that determines the width of your prediction intervals.
Yeah.
So aren't we kind of at the starting point then again?
Yeah, I mean, yeah, because, I think I understand your point. So, yeah, if your prediction is not good, then this means that your model is making a larger error. Therefore, it will produce a larger interval. And that's how it should behave, right? Because if you are making a larger error, you have to have a larger interval and you hope you capture the true value of your target variable. So that's how it is designed. I mean, conformal prediction is not necessarily tied to a point prediction. For example, in CQR, conformal quantile regression, you are just fitting these two different quantiles, right? Quantile regressors, and that's how you build your interval. So prediction interval, conformal prediction is like something that, it is based on the predictions, but it's something that sits on top of your the pipeline, right? And if it happens to be that your prediction is really off, and this means that your model is making a very large error at that point, and therefore, and the residual distribution, this 1 minus alpha percentile of the residual distribution is going to be large.
But sorry, no, that's my point, because if you're regressing in order to find this interval, if that regression is bad, then your interval is incorrect. Isn't that true? Like if you have this quantile regression prediction and the quantile regressors are just off,
Yep.
then it doesn't work.
Yeah, I mean, of course, you have cases where you won't capture your true value, right? That's the point. And that's why you say that if alpha is 10%, then you expect that in 10% of the cases, you won't capture it. So that's just a property of the approach. I mean, unfortunately, nothing is ideal. So you expect that you won't capture every true value using that approach. So we are just trying to have this coverage at this 1 minus alpha rate throughout the input space, right? And if we talk about split conformal prediction, let's say, yeah, then you can prove, actually, theoretically, that only in 10% of cases you'll miss your true value. So that's provable.
Time for one last question.
Thank you, very nice talk. My question is probably a bit related. Is some of these methods looks like they require a lot of data in a pragmatic way from your experience when they become reliable. So how much data do you need for some of these methods, particularly these tree-based methods to be reliable?
Yeah, I mean, the data sets that I've used contain both. Some of them are really small, like 1,500 samples. Some of them are really big, tens of thousands of samples. So it depends. And you might see that, so I haven't done that analysis, but what I've seen is that it's really hard to say that, okay, this doesn't work for small data samples. You can't say that. So because there are cases when it works for small ones, and it also works for the bigger ones. So it really depends on the use case. So I don't have a very definitive answer to that question, unfortunately. And depends on the quality of the data as well. Yeah.
All right, thank you. Please give Andrew another round of applause.
Thank you.